Teaching a large language model to handle open-ended tasks like creative writing, complex instruction following, or multi-step decision support is one of the hardest problems in modern AI. And the bottleneck isn't generation. It's evaluation. To train these models effectively, we need a reliable reward signal. But traditional approaches keep hitting walls. Human preference data is expensive, inconsistent, and hard to scale. Reference answer matching only works for closed domain tasks. And executable tests. They simply don't exist for most real-world prompts. So what if we stop treating evaluation as a post-hoc guessing game? A new framework takes a fundamentally different approach: prompt-level reward specification. The core architectural shift is separating the definition of success from the act of grading. Instead of asking an evaluator to reconstruct scoring rules for every single output, the system analyzes the prompt first. It builds reusable, task-specific scoring artifacts offline. These artifacts are then attached to the prompt and reused consistently across every response the model generates. Let's break down how this actually works under the hood. The framework deploys three complementary signals. First, deterministic constraint checking. When a prompt contains explicit, machine-verifiable rules, exact paragraph counts, required formatting, banned phrases, or structural constraints, the system doesn't rely on subjective judgment. It runs a two-stage pipeline. In the first stage, it scans the prompt and extracts hard constraints, intentionally filtering out anything too vague for automated verification. In the second stage, those constraints are compiled into lightweight, deterministic Python checkers or regex pipelines. These run independently of the language model. If the output violates a hard constraint, it gets a hard 0 on that dimension. This prevents reward hacking on surface-level features and guarantees that explicit instructions are actually followed. Second, we have the task-adaptive rubric. Think of this as a dynamic scoring matrix generated per prompt. The system analyzes the prompt's intent and generates a set of atomic, weighted criteria tailored to that specific task. These aren't generic checklists. They're structured into 3 tiers: critical gates that must be satisfied, core objective metrics that measure whether the primary goal was met, and differentiator scores that separate a functional response from a truly excellent one. Each criterion gets a categorical rating, yes, partially, or no, which gets mapped to a numerical weight. These individual judgments are then aggregated into a final quality score. Because these rubrics are generated once and cached, scoring remains perfectly consistent, regardless of how many responses are sampled during training or inference. Third, there's the holistic quality signal. Even if a response nails every atomic criterion and follows the format perfectly, it can still feel disjointed, overly verbose, or structurally weak. For that, the framework uses an independent global evaluator. This captures coherence, utility, natural flow, and response-level trade-offs. It acts as a safety net, catching systemic issues that isolated criteria might miss, like logical gaps, tonal inconsistencies, or missing context. Now here's where it gets technically interesting. These 3 signals, fine-grained rubric scoring, deterministic constraint checking, and holistic global evaluation, don't just sit next to each other. They're normalized to a shared numerical scale using robust scaling techniques to handle outliers and varying score distributions across different prompt types. Then they're scalarized into a single hybrid reward function, typically through a weighted summation or utility-based aggregation. This combined signal is fed directly into the reinforcement learning loop, providing a much richer, more stable gradient for policy updates. It covers local requirements, hard constraints, and overall quality simultaneously, which dramatically reduces reward variance during training and prevents the model from over-optimizing on narrow metrics. When tested, this architecture showed clear, measurable advantages. On offline benchmarks, the hybrid reward consistently outperformed standalone LLM judges, proving it can accurately rank response quality without leaning on noisy human preference data. More importantly, in online reinforcement learning setups, it drove consistent improvements across instruction following, creative writing, and decision support tasks. Ablation studies confirmed that each component is doing non-redundant work. Strip away the constraint checkers, and you get format violations. Remove the adaptive rubrics, and you lose task-specific precision. Drop the global score, and you start optimizing for brittle, checklist-driven outputs. Together, they create a training signal that's both precise and adaptable. By making reward criteria explicit, reusable, and multidimensional, this framework gives open-ended AI training a much clearer compass. It proves that when we separate what success looks like from how we measure it, we can build training systems that actually scale to the messy, creative reality of real-world prompts. As AI moves from toy problems to high-stakes, open-ended applications, having a transparent, technically rigorous way to measure quality isn't just a research upgrade. It's the foundation of reliability. Thanks for watching. If you're diving into the paper or experimenting with reward modeling yourself, drop your questions or thoughts in the comments, and let's talk about how we can make AI evaluation more transparent.